Okay, I think I'm live. So welcome to tonight's live stream looking at GCSE and A-level physics. I'm going to be doing these revision live streams pretty much 5 days a week between now and when your really important exams are, especially for students in Year 11 and Year 13. So that is, I guess, my main audience. Great to see so many people in the chat already saying hello to Joe, Matthew. I'm sure many more people are going to be joining in. If this is the first time that you've actually seen this live, then don't forget that if you head over to my website, which is GCSE Physics Online, I'm basically the guy doing lots of stuff with Lego to kind of teach you the physics. You can find here my kind of all the dates I'm going to be doing live streams. You can see what's coming up. Today is the 24th of April, so if you click on that, you can see that today we're going to be doing some questions about vectors and satellites in the GCSE stream. And for all of those of you who are doing A-level, you can see that today on the 24th, and this is on A-level Physics Online, again, loads of videos there to help you. You'll see that today, later on, we're going to be doing some stuff about radioactive decay and natural logs. So that is the plan, but obviously from this or these two websites, you can find links to all of the actual questions if you want to download them yourself. And obviously you can catch up with previous live streams. You can see what's coming up tomorrow and the next day and the next day. So I guess we may as well just get started. Again, if you're in the chat, if you've subscribed on YouTube, if you haven't already done so, do subscribe. The numbers kind of look nice when they get bigger and bigger. And obviously it means that more people discover the kind of stuff that I'm doing. And for people here asking about radioactive decay, that Dr. Carr, Dr. Ka, will radioactive decay be from year 2? Yeah, that's like the radioactive decay from year 2 in A-level, so like year 13. Okay, let's just begin with some questions though. So again, you can answer along at home. The first question, this is from one of my GCSE practice papers. It says that large ships are often towed by smaller tugboats when they start or finish their journey, and that means they can easily control their speed and direction. I'm quite happy with this. This is like the top-down view of an aircraft carrier with a load of, I guess, F-15s on it. Force is a vector quantity. State what is meant by a vector quantity. So when it comes to looking at vectors, what do we mean? Okay, let me just check my answers. Sorry. So, again, in the chat, this is like a simple 1-mark question. We did it the other day. Yeah, just like the scene in Top Gun Maverick, yeah, as Matthew says. Did I pick art GCSE? I actually did. When I did it, I did like art graphic design. So I got a grade A for doing like the art then. But this is more like a technical drawing rather than art, but yeah. Okay, Joe says, what is meant by a vector quantity? And basically it's a quantity with magnitude, which is the nice kind of scientific word, or you could say size and direction. And that means we often represent a vector quantity with an arrow. Somebody says, when are my A-level live scheduled? Basically down here, just down here on the screen, it should say that A-level is about 8 o'clock. So I'm doing like one stream, but the first half an hour is GCSE, the second half an hour is A-level. And that means I kind of get to do both in one stream. Okay, the tugboats pull the aircraft carrier using ropes. The force in the rope is called tension and is a contact force. Okay, state 2 more contact forces. So this question is actually a really simple one, which is basically name 2 contact forces, and then it's just kind of put into the context of the tugboats that we have up here. So in the chat, I know there's probably lots of people watching now. Can you put down the name of a contact force? Okay, so this one over here, we're just going to state them. So we're just going to write them down. We don't need to explain anything. What are some contact forces that we could put down? And there's a whole list that you could have. So somebody has said friction. Yeah, friction is a contact force, often where we have 2 surfaces in contact with one another. Okay, tension is a contact force, but that's already been given in the question. So we need to have something else in addition to tension. What else could we have? While people are putting stuff down there, another one that you could have is upthrust. Okay, sometimes this is called buoyancy, and that's the force of fluid around something that causes something to kind of maybe lift up. Other things that we could have include normal contact force. I'm just going to put down NCF for that. So maybe if you have a surface pushing back up on something, you've got this kind of normal contact force. Things that you cannot have, anything to do with weight is not correct, because weight is due to the non-contact force of the gravitational attraction between the two bodies. You can't have anything to do with magnets. So the magnetic force is not a contact force, and also the electrostatic. Okay, they're basically the three types of non-contact force, so anything else is good. Okay, it says here, now this one here is actually quite a difficult question. It says the tugboats pull on a larger ship with a total force of 200,000 newtons. Complete the sentence below using a statement from the box. So the large ship pulls on the tugboats with a force. Is it greater than, equal to, or less than the total force from the tugboats? So if the tugboats are pulling on the ship with a force of 200,000, what's the force of the ship pulling back on the tugboats? Is it going to be bigger? Is it going to be equal to? Or is it going to be less than? So this question, I reckon, is like a grade 8, a grade 9 question, even though there's only one thing that you actually need to write down. So this question is really due to Newton's third law, which is about the interaction between two objects. Now often it's stated as every force or every action has an equal and opposite reaction, which I don't think is a correct way of talking about it. A better way is to say that, you know, the force of A on B is the same as the force of B on A. It's the same size, but in the opposite direction too. And Aritz has got the right thing, which is they are equal to. Okay, so if we think about it, basically there's going to be a force in this direction of 200,000, and that's the force of the tugboats on the big ship. But the big ship is going to apply a force which is equal in size and opposite in direction of 200,000 newtons in the other direction. Okay, so what we actually have are the force of the boat on the ship, the force of the tugboats on the ship is equal to the force of the ship on the tugboats, and therefore the two forces are equal. Okay. Right, that one that was actually quite a tricky question, but that's to do with Newton's third law. Okay, the next question then. The two tugboats are now used to turn the large ship. They pull with two different forces as shown in figure 2. So what we have is 50,000 newtons east and 80,000 newtons north. Okay, now if that's to the east and that's to the north, and again this is kind of looking down, then that means these two forces are going to be at right angles. And the next thing we need to do is draw a scale drawing and use it to determine the resultant force on the boat. Now, I would say looking at this, because you've got force to the right and the force up, the resultant of these two forces is going to be to the right and it's going to be up. Okay, so what we need to do is actually think about drawing that in a scale drawing. So we happen to have a grid here, and I'm going to start at the bottom left-hand corner. And what we're going to do is we're going to represent each of these forces with a vector arrow. I'm going to do it in pencil. First of all, in case I make a mistake, I'm going to use a ruler. And the first thing we're going to do is we're going to draw a force that represents this 50,000 Newton force. So I'm going to say that 1 square is equal to 10,000. Okay, and so I'm going to get my ruler. And I'm going to go along 1, 2, 3, 4, 5 squares. Okay, I'm going to sort of go over that a few times to make it clear for the camera. So hopefully all of you can see that. Okay, and what I've said is 1 square is equal to 10,000 newtons. So I've just written down my scale there as well to make it really clear. Now that's the force to the east, but we've also got a force going to the north. And this is going to go up a total of 8 squares to represent my 80,000 Newton force, which is in the northerly direction. So again, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. By magic, the kind of squares that we have there happen to fit my scale diagram perfectly. And so this arrow up here, I'm just going to label this. So we've got 50,000 newtons east, and we've got 80,000 newtons north. Okay, now what's the resultant of these? Well, we can work out the resultant of lots of different vector arrows by basically going from the very start to the end. So what we've done is we've basically added one force arrow to another force arrow. And now we're going to go from start to finish. Okay. Hold on, that's not the best line. And we're basically going to go like that from start to finish. Okay, and I'm going to call that FR to be my resultant force. Okay, so that's the first thing we can do. Now there's two ways of doing this. It does say by drawing a scale diagram, we can work out this resultant force. Now, of course, as somebody said, we can use Pythagoras. So we know that a squared plus b squared is c squared. So we could say that FR is going to be equal to the square root of 50,000 squared plus 80,000 squared. Okay, so that is, I think, the best kind of mathematical way of doing that. So I'm just going to do 50 squared plus 80 squared, square root that, and that means this is equal to about 94,000 newtons. Okay, now that's one way of doing it, but the question does say to use scale drawing. Now the thing is, on the actual graph, when you print it out normally, 1 centimetre is equal to 1 square. So if you measure the distance here, if you know that the answer was equal to 9.4 centimetres, so that's equal to 9.4 centimetres, and 1 centimetre is equal to 10,000 newtons, then you just multiply 9.4 by 10,000 to find out that this is actually 94,000. Now the second thing we need to do, in addition to the size of the force, so this is the magnitude, because it's a vector there must be a direction, and we're going to look at the bearing from north. So we want to know this angle in here, which I've just put down as theta. So it tends to be like you've seen in GCSE maths. If we look at a bearing, it goes from north. And to work that out, you need to use your protractor. And especially for AQA students, when you're doing paper 2, make sure that you buy a protractor. So if I put this in here like that, I reckon that's about kind of 31, 32. I reckon, let's just kind of zoom in a little bit more. I reckon that's about 32 degrees. So I reckon the bearing from north is 32 degrees. But again, often what we do with the bearing is we give it as 3 numbers. So 032 degrees is the right kind of answer. Temedola, this guy's way better than any tutor. Thank you very much. I mean, basically, this is just maths. Well, sorry, this is just physics tuition, load of maths in it. But yeah, this is basically completely free tuition for an hour every single evening. So yeah. Do you get all the equations for AQA GCSE 2024? You get, I think, all of the equations given to you, but it's really down to you to be able to recognise and actually select the correct equation for the actual exam. Okay, so they wouldn't give you an equation for something like this. I don't think they give you the equation for Pythagoras. They wouldn't give you any trigonometry stuff. So if you wanted to use maybe the adjacent side, the opposite side to look at finding tan of an angle, they wouldn't give that to you, but they would give you the physics formula. Okay, so the bearing from north is the 032. I suspect for a GCSE paper, if you put down 32 degrees, or maybe within 2 or 3 degrees of that, you'd get the marks. Okay, and so therefore you'd get your marks for doing this, and obviously showing that kind of scale diagram. Will I be able to answer specific questions, or we have now, or is it just past paper questions? I will try and answer questions kind of related to what I'm doing. So if you do have questions, put them in the chat, and I will try and answer them. Obviously, I can't guarantee that. This is stuff I will definitely do, but if you ask smaller questions, I can answer them throughout, or maybe at the end of the question. Right. The boats all turn off their engines. They gradually stop moving. Explain using the idea of forces why this happens. So why is it that that boat in the ocean is sailing along, the engines get turned off, why does it keep moving? Well, basically, it's going to keep moving because I suppose initially it was moving, but now there's going to be a resultant force is now due to drag, and that drag could be due to water resistance or air resistance. A resultant force is now due to drag, and this is in the opposite direction to its velocity, so it decelerates. Hopefully you can just about read that. Okay, and because it's decelerating, because of this resultant force in the opposite direction to its velocity, so here's the kind of boat, it's moving in this direction with a certain velocity. There's no force, there's no thrust driving it forwards, and that means the only force on it is going to be backwards due to drag, water resistance and air resistance, and that means there's going to be a negative acceleration, and that means it slows down. Okay, there we go. That was the first question. Actually, I don't think that was too bad, but there were some tricky parts within that. Now, the next question is about satellites, and this is very much more of like a kind of triple science kind of topic for those of you, and this is like a paper 2 question, but I reckon all of you watching this can have a go at this question. Does anybody have any questions at the moment, though, in the chat? I know some people, like Zenatin was asking about if I can answer certain questions. If you have anything, just put it down now, and I'll see if I can just briefly answer those questions. But I would say for everybody watching, if you haven't really done so, go and buy a brand new protractor, a nice clear one where you can actually see all the numbers. They don't cost that much. If you order it today or tomorrow on Amazon, you'll have it for the weekend and plenty of time for your exams. What is a white dwarf? Okay, so a white dwarf is basically a star that's kind of towards the end of its life. Often it's something which is still really hot. And this, maybe something after it's been like a red giant or something. It kind of all collapses and we have this really kind of dense, hot core. And what it's doing, it's radiating light and energy out. So that's why it's glowing white. It's really hot, but it's really, really small. Okay, and over time, that can then become a black dwarf as it kind of has radiated out its energy, just leaving this kind of duller star behind. Okay, so... Right, so people don't know how to do this question. So let's just think. First of all, you've got to remember that when you're in your exam or when you're doing past papers, it is only GCSE physics. And that means the mathematics is going to be a lot easier than your GCSE maths exam. It is only GCSE physics, and for anybody who's doing A-level physics at the moment, you might agree with me that once you start doing A-level, GCSE seems relatively straightforward. And because of that, the maths is actually relatively straightforward. So, the first question is about artificial satellites, and it gives you lots of information. It says there are artificial satellites in orbit around the Earth. Geostationary satellites move in a circular orbit, and their distance is 36,000 kilometres from the centre of the Earth. Calculate the speed of the geostationary satellite in meters per second, giving your answer to 2 significant figures. Now, the one bit of information you need to know about this is that because it's geostationary, then the time it takes to orbit the Earth once is equal to the time that it takes the Earth to orbit or rotate one time as well. So what we need to know is we need to know the time for it to go through one full orbit, one full rotation. Now we call this time capital P because it's the time period. Just like when you're looking at waves, we look at the frequency and how that's related to the time period of the wave. And this is going to be equal to 1 day. Now 1 day is equal to 24 hours. And that's going to be equal to 24 times 60 minutes times 60 seconds. And that's going to be the time period. Okay, so if we want to know the time period for one rotation, that's equal to 24 times 60 times 60. Oh, sorry, 24 times 60 times 60. And so the time period is 86,400 seconds. Okay. Now, the next thing, as Ashay says, Distance equals speed times time. Yes, that's correct. So this is an equation, I think, given to you in your data sheet. Or we could say that the speed is equal to the distance or displacement divided by time. Okay, now that's where I'm going to write it. So v is our speed, s is the distance, and t is the time. Do we know the distance around this? How do you work out the distance from the information in the question? Well, in the question it says they orbited at a distance of 36,000 kilometres from the centre of the Earth. So what we do know is that from here to here is 36,000 kilometres, which is 36,000 metres. And that's just equal to the radius. And Joe Smith said, yeah, 2 pi r. O'Shea said pi 2r. Yeah, we've got the circumference, d pi from Katzor. Yeah, all of these completely correct. So the distance it travels is going to be equal to 2 pi r. And it goes around this circumference in a time equal to the time period. So then we know this. This is just speed equals distance over time. So the distance is going to be 2 times pi times 36 million. And we're going to divide that by the time period, which is 86,400. So we've got a massive distance in a massive amount of time. And then all you need to do, and I would suggest everybody get your calculators out, not your phones, but use your calculators from now on for every single calculation. So it's just completely automatic, everything that you're doing. So we've got 2 times pi times 36 million. Divide that by 86,400. How come the distance isn't from the centre of the Earth? It is, yeah. So 36,000 kilometres from the centre of the Earth, and here we have the centre of the Earth up to that satellite. To be honest, if we were to include the radius of the Earth, which is about 6,400 kilometres, it would change that, and often at A-level they tell you about the height above the ground, but here they've given you the distance from the centre of the Earth for that. And that means the answer is equal to 2,618 metres per second. Okay, so that's the answer that I've just worked out. I would say that probably a more appropriate answer could be something like maybe 2,600, or even 2.6 times 10 to the 3 metres per second. Okay, so I guess we've kind of been given the distance is about 36,000. Also, for this question, like a lot of stuff with GCSE, we've made some assumptions. We've assumed that it's going in a perfectly circular orbit and it's not elliptical in any sense. So yeah, it's going pretty quickly, but then that's just what they do. And actually, things which are closer to the Earth actually orbit with a shorter time period and are actually going quicker. So what we find is as things go further away, as the radius increases, the time period doesn't doesn't increase by the same amount. So it goes. Things which are further away are travelling slower, and things which are closer are travelling faster. Okay, hopefully that's all making sense. Howlin, the birds, Joe. Is this astrophysics? Yeah, I guess this is kind of to do with like the space module for GCSE, but I would say that actually this one here is kind of like just a speed equals distance over time calculation. Okay, right, the next question is still about satellites, but really a lot of physics is all completely linked to each other. So this question says that a satellite in orbit only has a single force acting on it. How can a single unbalanced force allow a satellite to travel at a constant speed around the Earth? Okay, so this question here, normally when we have unbalanced forces, we have objects which can get faster or they might get slower, like the tugboat example that we had. So how can that unbalanced force not change its speed? Well, the first thing I'm going to do is draw my satellite. There we go, just a quick picture of a satellite. And let's imagine the satellite is moving at this point in time in this direction. Okay, so it's going to the right. What we have is a force inwards due to the gravitational attraction of the Earth. And this force at any time is going to be at 90 degrees to the direction that that satellite is moving in. If I just get back my piece of paper, so at this particular point here, the satellite is moving at a tangent to that part of the circle. The force in is going to be directed towards the centre of the Earth due to this gravitational attraction, and therefore these two things are going to be at 90 degrees. And what this means is that the force is at 90 degrees to the motion, and therefore, I'm just going to write that down, the force is perpendicular to the motion, or to the velocity. And that means it doesn't change its speed, but instead it still accelerates it, not by making it faster or slower, but by changing its direction. So the force is perpendicular to the velocity, so its speed stays constant, but its direction changes. So basically it's still accelerating towards the Earth, but it's still travelling through the same number of meters every second. Okay, hopefully that helps. We then have a question about, and this is kind of just trying to put it, why was somebody on timeout? Only because there's like a comment which I think somebody else might have taken offence to. So basically, if anybody sort of says something in the chat that's bad or maybe a little bit like dodgy, I just kind of tend to put people in timeout. Of course, if it's really bad, then I'll just ban you forever. But I know it wasn't meant in any harsh way. Okay, right. Not available says speed is a scale of quantity, so it doesn't change the direction. But the velocity changes because the direction changes, and therefore it's accelerating. Not available, perfectly correct. So what we have is something accelerating, and therefore we have something under circular motion. So NASA have designed a spacecraft to visit the moon. It starts off in orbit around the Earth. Explain using forces how it can move from an orbit around the Earth towards the moon. So for example, if we had another thing, so this is something in orbit around the Earth. This is our new NASA spacecraft. How do we get it to go from here out much further away to where the moon is? Okay, so what we have is we basically need to do something to this to actually cause it to maybe speed up, and as it speeds up, it kind of takes this kind of like other path here, which is more of like a spiral outwards as its distance from the Earth increases. So what we could say, explain using forces how it can move from an orbit around the Earth towards the moon. We could say that maybe thrusters, I can't speak and write at the same time. Thrusters exert a force on the rocket, and this causes its speed to increase. And of course, as its speed, here we go, got some good questions. I'll answer a lot of these in a second. So there's going to be a force exerted. If you have a force, it's going to cause some acceleration if there's this resultant force. As it accelerates, in this case, the speed increases. Now, the force of gravity, or the force due to gravity, stays the same size. And is not large enough to keep this faster object in maybe a constant orbit. Okay, so before we kind of had this picture here, and basically this force provides a centripetal force which depends on how quickly that thing is moving. Now, if you've got something where you still have the same size force, but it's travelling at a much bigger velocity, that force isn't going to be enough to keep it going in a circular path, and that's the point at which it kind of sort of spirals away from the Earth and goes out towards the moon. Okay, I reckon, Mansour, there's a good question there about escape gravity. I think the better thing you might be talking about is escape velocity. And as somebody else said, when you've got a high enough escape velocity, then effectively the kinetic energy is going to be greater than the gravitational potential energy at that point, and it can escape the orbit of that. Right, is this a past paper? Jason T, good question. This is actually a paper that I put together. So these questions, I worked with some other teachers. They helped write some of the questions, so it wasn't just me doing all of that. I made all of these papers. So basically they just wrote some of the questions in a Word document, and then Rufus worked with me. He started formatting these, and then I spent hours and days, and basically it's done on PowerPoint. So PowerPoint is super flexible. It's easy to change the order of things around. It's easy to copy stuff across. You've got the same thing on page after page. So this is all on PowerPoint, just drawn with different boxes. There's actually if you scan that, if you do have a mobile phone that's got a barcode scanner, you can actually scan the barcode like real exam papers have. All of these pictures were drawn using PowerPoint. So this is just like a grouped selection of objects, but I think it gives me lots of flexibility. And for those of you doing A-level, and you've seen this book here, everything here was drawn in PowerPoint as well. So things like this picture here for a gold leaf electroscope, it's just a really simple, easy way to have lots of control. And sometimes simple things are the best. Can I get you a grade 9 with these papers, Timidola? I reckon, yes, I can. I reckon if you use the papers, that will give you one of the best chances of getting a grade 9. Of course, having the papers is one thing, but you've got to sit down and work through them and just get on with the work. But I've got 12 papers, 6 for paper 1, 6 for paper 2. And if you buy the lot, I reckon that's going to really, really help you deepen your understanding of the GCSE physics. What book is that? Just a Person. This is actually a book for A-level physics. For anybody who's thinking about A-level, there's basically books 1, 2 and 3 which cover all of AS physics. Book 4 goes into so basically book 4 starts with like the kind of stuff at the end of year 12 into year 13. Books 5 and 6 aren't complete yet, but I will be doing those as soon as the exams finish this year, and these are going to be for year 13. But basically book 1 has questions from July onwards over the whole summer holidays, and if you do book 1, that means you're going to start A-level physics really, really well. What kind of pen am I using? I'm using a Pilot V-Sign. Okay, and it just writes beautifully. Okay, but although I'm actually writing like this with a Pilot V-Sign, when I've got the answers here, these have been written on my iPad on Notability. Okay, right, so I reckon I'm going to leave it there. The slow-mo, thank you so much. Glad it's inspiring a bit. Okay, Katsura, yeah, buy the papers. They're not much. You can easily get them in my online shop. These exam papers are based around the AQA spec, because I think that's what about 85% of people are doing. But these things here, they are really, really useful. The slow-mo, was I inspired by the Corbett Maths 5 a day? Yeah, do you know what? I saw the 5 a day, and that's why I call this a daily workout. So every day, you just have some questions to do. Corbett Maths, yeah, I think that was really, really good. And I know he's got a 5-day book. I actually bought one for my daughter. She really enjoyed using it a bit. But this is like even more detailed. This kind of, I thought it would be an easy thing to do, but yeah, by doing the questions like this, it's taken a long time. But basically, every day, if you're doing A-level, there's questions for you. So today, if you're doing A-level, just do this question here. That's you done for the day. It only takes like 5 minutes. Tomorrow, do this. The next day, do this. And basically, by doing 5 to 10 minutes of questions a day, I guarantee that you'll get better grades. Okay, right. I'm afraid there are... So, right. Okay, let's see what's going on here. Okay, right. Let's move on and start doing some A-level physics. I know I'm a bit later. This is now, Jamil, A-level content. I was just chatting, answering people's questions. Loads of people in the chat. Right, let's just stop doing too much stuff. I'm just going to just put a couple of people in timeout. Right, so 31st of July. These are the questions which have come from book 4. Okay, so the questions here are about radioactive decay and also looking at natural logs. Now, the other day, a couple of days ago, I did a stream where we basically had some data about a dice. So we've got the number of throws, the number of dice remaining, and we basically plotted a GCSE graph. So this shows as time goes on, the number of dice gets less and less each time. It goes down by about a third each time because we remove the 1s and 2s, leaving the 3s, 4s, 5s and 6. So basically, we've got about a third of the dice being taken away and 2/3 remaining. And looking at this, we said the half-life was about 1.7 throws. That's the time it takes, or the number of throws for half of those dice to decay. Okay, now the stuff I'm doing today is, again, the kind of question that you could be asked in a question about radiation or radioactivity. It also is maybe like a paper 3A style question. And I think this video is suitable for anybody doing A-level physics in year 13. So Edexcel IAL, so Aisha, yes, this is suitable for you. It's suitable for AQA, OCR, Edexcel. I'm trying to make my stuff at the moment basically suitable for everybody. Because a lot of A-level physics is going to be absolutely identical. Okay, so 100 dice were thrown into a container. Those that landed with a 1 or 2 showing were removed and the remaining dice thrown again and so on. The following data was recorded. We then have the kind of style of question you get in an A-level physics exam where it says it's been suggested that D is equal to D naught e to the minus kn. Okay, so everything is explained underneath. So we've got the number of dice, the original number, we've got n is the number of throws, and k is just this constant. Now the first question is easy. Okay, year 13 is A2, that's correct, yeah. The first question is we need to work out the natural log of the values of D. Okay, so all we need to do is put the numbers into the calculator. So the first one, we're going to look at the natural log of 19, and that's equal to 2.9444. So I'm just going to write this down as 2.94. The next one is natural log of 14, 2.64. The natural log of 8 is 2.08. Then we have the natural log of 5, 1.61, and then we'd have 1.39, 1.10, and 0.69. Okay, now really with these, I think what it's interesting is that basically this is kind of 2 significant figures. So that's going to be 2 significant figures for that data, and that means we need to give this data ideally to 2 decimal places. Okay. This one over here, yeah, just Joe, like Joe says, just punch the values in the calculator. Moodle Mip says that you always make silly mistakes. Yeah, this is like where it's easy to make mistakes. I guess strictly speaking, the last ones here, these were to 1 significant figure. So really these should have been given to 1 decimal point. But, you know, I just sort of kept it consistent down here. And this does look like an A-level maths question. I don't know how you say it. Exiba? Is that how I say your name? Xhibah. I don't know how to pronounce that. So, yeah, basically it is like A-level maths. It's the same thing. Take the natural log of both sides of the equation. So this one is just a maths question. Yeah, so Light says, basically when you've got log values or natural log values, if the number is to 2 significant figures, you give your answer to the number of decimal places as there are significant figures over here. Okay, that's just kind of one of the rules. Okay, right, take natural logs of both sides. So we're going to take natural log of D, and that's going to be ln D. And that's equal to the natural log of D naught, so that's natural log of D naught. And then, because we've got the natural log of e to the minus kn, that becomes minus kn. Okay, if you're year 13, you should know how to do that. Also, if you were in my live stream the other day, I think we did exactly the same thing over here. So again, this is the point in the book that basically I kind of build stuff up. So you did it here previously just by following the pattern, and then you do the same question over here. Right. Right. Do people want me to explain about the rules for logs in terms of significant figures and decimal places? If you want me to, I can go over that now. Okay, what's k? K is just a constant. Okay, so it just says over here that for this particular dice, when we take out a third of the dice, k is just a constant for that. Okay, yes, right. I'm going to go through the rules for logs, right, and I'm going to show you this to you because I think this is super important and it's not obvious, right? I'm going to do okay, so let me just write down a number. So let's have 1.234. Okay, I'm also going to have the number 12.34, 123.4, and 1,234. Okay, so if I take logs of these, so this is going to be log to the base 10, so this is just number n. If I take the log of that number, log of 1.234 is 0.09132. Okay, if I take the log of 12.34, the answer is 1.09132. Okay, if I take the log of 123.4, the answer is 2.09132. And I'm going to do the same for this. Although actually, I'm sure all of you realise that without using a calculator, what's going to be the value of log 1,234? Okay, so let's look at the pattern, people. What is going to be the log, without using a calculator, of 1,234? Okay, I know people are just typing this in at the moment. 3.0913, so 3.09132. And if we had 123,400, if we did that, so the log of 12,340, so the log of 12,340 is equal to 4.09132. Okay, basically the first number here, okay, the first number tells you about the size. Okay, so look, this number just tells you about the size of that number. Okay, and therefore it's not significant. Okay, instead, what's significant is going to be kind of what's over here. Now really, if this number is given to 4 significant figures, then you should give this answer over here to 4 decimal places. Okay, so 4 decimal places in this case would be 0.0913, 1.0913, 2.0913, and so on. Okay, so basically this number here, the 0913, kind of relates to the 1, 2, 3, 4, and the number in front just tells you about the size of this. Okay, because as somebody said, this is basically something times 10 to the 1, that's times 10 to the 0, times 10 to the 2, times 10 to the 3, and times 10 to the 4. Okay, so basically, this thing here is basically 1.234 times 10 to the 4. Does that make sense? This number here is just 1.234 times 10 to the 4. And when you take the log of it, the 4 basically comes down in front to be like the 4.0913. Okay, so n is just like a random number. But what this means is that if you had maybe some data where you had like 23.2, and then you had 25.6, 27.8. So this is maybe a value of x. If you had to work out a value of log x, what you'd be doing here is looking at this data, thinking that's to 3 significant figures, and therefore this has to be to 3 decimal places. So you see that so if you took like log 23.2, that's equal to 1.365. Natural log of 25.6 is 1.408, and the log of 27.8 is 1.444. Okay, basically all of these have a 1 in front of them because these are all something which is in the order of times 10 to the 1, and therefore the first number doesn't add to the significance. So effectively what we have is over here we've got 3 significant figures, and that means when you take the log of that number you need to give it to 3 decimal places. Okay, hopefully that makes sense. Yeah, okay. Why do you work out the log of it though? Quilila? Because the question has asked you to. So basically, when you have a log value, whatever the number of significant figures is, display that number of decimal places. Hopefully that makes sense. So there's a reason behind everything. Right, plot a graph of the natural log of d against n. So this is the thing that we've been asked to do. So we've got a big piece of graph paper here. Hopefully that all fits in the screen. So when the number of throws is 0, the natural log is going to be 4.61. So I'm just going to do this fairly quickly. When it's 1, it's 4.16. When it's 2, 3.83. When it's 3, it's 3.37. When it's 4, it's 2.94. When it's 5, it's 2.64. Hopefully this is all good. Good luck for people doing SQA High Physics tomorrow morning. Tethies, yeah, good luck. Hope that's all goes well for you. Number 6, 2.08 is around here. 7 is 1.61. 8 is going to be 1.39. 9 is going to be 1.10, and 10 is 0.69. Okay, so basically what we now have is yesterday when we plotted d against n, we had this exponential decay curve. Now, when we've got the natural log of d against n, we have a straight line. Okay, so obviously the next thing is to get your ruler, to line it all up, and to draw in a straight line. Now, normally, this all works pretty well. Is it frozen? Am I frozen? Hopefully not. Can everybody see me and hear me okay? No, it's not frozen, says the birds. Not frozen for me. Cool. Okay, good, fine. Phew. When the technical stuff goes wrong, it's so annoying. Okay, right. So basically I'm just going to do a line of best fit, which looks basically something. It's a bit difficult where the ruler's not quite long enough. Okay, so I've done my line of best fit. That's not the best one. It probably should be a bit higher up there, but hopefully that's okay. So we've plotted the graph. We've drawn in a line of best fit, a straight line, and now we're going to calculate the gradient. Now, I suspect that if I ask you to work out the gradient, most people are going to get it correct, but about 30% will incorrectly work out the gradient. Now, of course, we need to draw in a big triangle. So the gradient is going to be equal to our change in y over our change in x. Now, the y value goes down here to about maybe 0.45, and we're going to take away the value up here, which is about 4.6, divided by 10 minus 0. So when we do that, and this is the thing that I know so many people make mistakes on, so 0.45 minus 4.6 divided by 10 is equal to minus 0.415. Okay, this is a negative gradient. Don't forget that. Don't just do 4.6, take away 0.45. Do 0.45, take away the starting value, which is 4.6. So that is our gradient. Okay, so the gradient of the line, I'm just going to write it down here again, is minus 0.415. And then we're going to use the gradient to determine a value for k. Okay, and this is why we take the natural log of data, because it allows us to use a straight line graph to find a constant. Now, on the graph itself, I'm just going to write it down over here. On the y-axis, we have the natural log of d, and on the x-axis, we have n. Now, we know that the natural log of d is equal to the natural log of d naught minus kn. And I'm going to rewrite this, where because we know that this is the y value and this is the x value, I'm going to rewrite this as natural log of d is equal to minus kn plus the natural log of d naught. Okay, and the reason I'm doing that is it frozen? I think it's all right. Okay, I'm just going to keep going. We've got y is equal to mx plus c. Okay, so what this means then is that on the y-axis we have the natural log of d, on the x-axis we have n, and this means m, the gradient, is going to be equal to minus k. Okay, now the gradient is what we calculated up here. So this value here is equal to the gradient. So we can say that minus 0.415 is equal to minus k, and that means 0.415 is equal to k. Okay, that's all good. That's all it is. So basically, we can use the value here to determine a value for k, and then the other thing we've been asked to do is calculate the natural log of 2 over k and compare this to the value of half-life that I calculated yesterday. So what we're going to do is we're going to do the natural log of 2 divided by our value of k, which is 0.415. And if we do that, we find that this is equal to 1.67, or about 1.7, which happens to be the half-life. So this is also equal to the half-life, because effectively what we've worked out here is the value here for the k is a bit like the decay constant. Okay, so this value of k basically tells us the decay constant. And yeah, so the gradient is equal to the decay constant. And if you do the natural log of 2 divided by the decay constant, we get the half-life. Now, yesterday, when we actually plotted the graph, what we found was the time it takes for the number of throws for that to go from 100 down to 50 is equal to about 1.7 throws, which is there for the half-life, t a half. And that's what we've calculated properly today, using this method as well. So effectively what we have here, although it's a question about dice, it's really about exponential decay. And you can see how this equation here is kind of similar to a is equal to a naught e to the minus kt. Sorry. This equation over here is very similar to a is equal to a naught e to the minus lambda t. Okay, but rather than t we used n, rather than a we used d, and rather than lambda we use k in this example. Do you have to know it's the natural log of 2? You don't need to know why, but I do have it over here. So where was it? I did it the other day. Where is it? There. You don't need to know it, but I think if you're wanting the top grades, then you can work out why that is. Sorry, I've got it here. So basically, these are my derivations. Half-life, it's about halfway through the book. Yeah, basically, to derive this equation over here, you basically start with the equation here for the activity. when the activity is half the original amount, then the little value of t is going to be equal to the half-life, and therefore you can do all of this to find that. Okay, and it comes from, all of that stuff that people have said. So if you want to see the derivation, I did that 2 days ago on the stream, I think, or was it yesterday? Was it yesterday? I don't know. It just blurs into one endless stream of A-level and GCSE physics. But if you want to find these derivations all set out like this, you can find this derivations book. Tell you what, these notes here, I don't sell them. These are completely for free. And I reckon if I just go to... Let me just go to a new tab and I'll just find this. So I did it the other day in one of the live streams. I think I've got a link, but what I'll do is I'll put that link into the chat now. Okay, so if you go to that link I've just put in, that will give you basically a free way to kind of get access to the full booklet of all these derivations. Do you need to know how to derive everything, Ethan? No, you don't. Some of it I think is just interesting because that's what kind of gets me excited. But I think it's a good idea if you've got the time to know where things come from, because that gives you a much deeper understanding. So rather than just seeing an equation that says, like the activity or the decay constant is equal to natural log of 2 over the half-life, you think, well, why is that? There's always a reason behind everything. Okay, but I think there are some that you do need to know how to derive. I think one of them is, and I think these are all outlined quite clearly. I think this is one of them, to do with looking at a double slit for AQA, if you want to derive that. Is there a possibility of me doing a live stream where I go over a paper 1, please, for AQA? I'm definitely going to be doing more topic-specific stuff as we get nearer to the exam, but you can kind of see what I'm doing. So if you want to find out what on earth I'm doing for the next few weeks, what I've done, and I will be doing stuff like before paper 1 and paper 2, is, let me just put in my passcode without everybody seeing it. If you go to alevelphysicsonline.com, click on the live button or just look at the description underneath this video, then you will find what I'm doing for the next few weeks. So you can find the topics, you can download stuff. I've also just put up this evening what I'm doing next week. So next week I'm going to be doing some stuff to do with paper 3A, some practical stuff to do with simple harmonic motion, F equals Bill, Planck constant practicals, so some good revision for year 12 stuff. So you can see what I'm doing. But obviously when I do stuff like this, I try and answer people's questions and I talk about other topics within that. Right. Hopefully that helps. Hopefully some people have got something useful out of tonight. If you haven't already done so, you can buy practice papers for A-level at my shop, which is physicsonline.shop. You can buy those, and I've got some practical questions which are good for Edexcel and OCR as well. I've obviously got the premium plan on my website if you want to access all the videos, which will give you a really good chance of just revising and learning everything that you need to. And of course, there's loads of good stuff and loads of good free stuff as well. So keep looking around. I hope all of you are doing okay as you're revising. I've got plenty of stuff to support you on my website, and I'm sure that your teachers will be supporting you as well. So if you're not sure, speak to your teachers, arrange a time to meet them, give them specific questions. So don't just say, I don't understand it. Go in with specific questions you've already started working on, and that's going to get the most out of your time and their time as well. Can I flip the camera so you can see the stream setup? No, to be honest, because I've got everything like fixed in position now. So I've got like basically a digital SLR looking at me. I've got another digital SLR that's kind of looking down on the table, both of which are kind of fixed in position. And then I've basically just got loads of bits of paper and books and everything everywhere. So it's just basically a fairly clean setup. But then when you look on the floor, it's just covered with bits of paper. I've got pens and stuff to the side of me, but yeah, it's all good. Right, do I have any predictions for real exams? No, just learn everything, revise everything. Don't try and predict what's going to come up. The people who are going to do well are the people who understand the full course and everything in it, rather than leaving out bits as they're revising. So my advice would be to revise everything, do as many past papers, and just do every question that you can possibly find. Hopefully that helps. Goodbye, and I'll see all of you again tomorrow. Hopefully I won't be late tomorrow. I'm in London at a British Physics Olympiad event. I think my train gets in, and then I've got just enough time, if the train gets into Bath on time, for me to then get back to my office and actually film. So I will be in London tomorrow, so I might meet some of you there, and then I'll be back here tomorrow doing another stream. Thank you everybody, and goodbye.